Couple other things. We're going to cover this in a little bit, but I do want to put it in this context. So there's this thing called hybridization. You need to understand it a little bit, but before you need to understand it, I would highly recommend you just know how to assign it. Here's the way this works. How many s orbitals are there in any particular shell? Well, there's 2 electrons, but how many orbitals? Just 1. How many p orbitals? 3. Can hold 6 electrons, but just 3 orbitals. And then you're going to have 5 d orbitals. This idea of hybridization comes from when you mix orbitals. And when you mix orbitals, you make new orbitals. Like if I mix an s and a p, turns out you end up making new orbitals that have a slightly different shape. It's 50% s and 50% b, which is why they call them hybrids. So we'll talk more about where that comes from in a minute, but here's what I want to get across. Whether you know ultimately what this means, more important to answering a test question is how to assign it. And it's assigned simply based on the number of domains. So like here, how many domains does carbon have? How many? How many domains? Electron domains? Not 3. 2 directions. 2 directions. With 2 electron domains, what that means is he needs to make 2 hybrids, turns out. To make 2 hybrids, the number of hybrids you want to make is always the number of orbitals you need to mix. So 2 domains, 2 hybrids, he needs to mix 2 orbitals. You always mix the first 2 available from left to right, from low energy to high energy. What are the first 2 orbitals available? An s and then a p. And so for 2 electron domains, you mixed an s and a p. And so we call the hybrid orbitals or the hybridization just sp, just what you mixed. Okay, let's go over here to boron. How many electron domains here for boron? 3. 3 domains means he needs 3 hybrid orbitals. 3 hybrid orbitals means how many does he need to mix? 3. What are the first 3 you can mix? An s, a p, and another p. And rather than calling it spp, because that kind of sounds terrible, right? They call it sp2. Because you mixed an s and 2 p orbitals to make it. So for 4 domains, whether it's the carbon here, the nitrogen here, or the oxygen here, 4 domains, 4 hybrids, sp3. 5 domains in all of these cases here. Doesn't matter which central atom you want to look at. Well, sp3d. Good. After your third p orbital, you're out, and you got to go to d's. And so the central atom is going to be sp3d. And then 6 domains, either case. There's first 4 orbitals, but 6 domains, I need 2 more. Awesome, sp3d2. Either case for the central atom. That's its hybridization. And that's also how many of those hybrids it has. Notice 2 domains, either one of these cases, meant sp hybridized. But if you're sp hybridized, that means you mixed how many orbitals? 2, an s and a p. And if you mix 2 orbitals, it always creates 2 hybrids. You don't just get 1 sp hybrid orbital, you end up creating 2 of them. So if you're sp2 hybridized, how many sp2 hybrid orbitals do you actually have? You're always going to have 3. If you're sp3 hybridized, how many sp3 hybrid orbitals will you have? You'll always have 4. sp3d, you'll always have 5 of those sp3d hybrids. sp3d2, will always have 6 of those sp3d2 hybrid orbitals. So sulfur, we'd say is sp3d2 hybridized, and he has 6 sp3d2 hybrid orbitals, same as the number of orbitals he mixed to create it. Now what hybridization again means, we're going to talk about that a little more in a little bit, but first I just wanted to show you that from the number of domains, you can get the electron domain geometry, you can get the bond angles, and you can get now the hybridization. And then you can take it a step further and try and figure out what the molecular geometry is as well, based on any non-bonding domains. So you already know how to determine the hybridization from the number of domains. Awesome. That's what you want to use. However, you should have just a little bit of conceptual understanding of the hybridization model. So here's the way this works. If you look at carbon, carbon's valence electrons are 2s2, 2p2. These are the electrons we show in the Lewis dot structures, the ones that are going to be used in the bonding, right? And so if we look here, carbon 2s and 2p. You know what, let's give a little contrast here. So classical bonding theory says that an atom, like carbon, will use his unpaired electrons to share and make bonds. Based on that classical theory, how many bonds should carbon be able to make? So again, an atom will share its unpaired electrons to make bonds. Well, 2. He's got 2 unpaired electrons. Those are paired. And so classical theory might predict that carbon makes 2 bonds. Well, we have a problem, because we predicted this earlier, and if you go back and look, carbon needs 4 more electrons to fill his octet, and in any structure you draw, carbon usually ends up making 4 bonds, just like that. And so classical theory has a problem here. And what we figured out is that carbon takes this electron right here and puts it up in the 2p orbital. He promotes it. It's a little higher energy. So notice if you get a promotion in a company, you end up with a higher position in the company. Well, this electron is getting promoted to a higher energy orbital. And so now carbon ends up with 4 unpaired electrons, and he can now make 4 bonds. And the idea is he had to spend a little energy here, and this is a higher energy configuration than this one. And the universe wants things to be low energy, not higher energy. But the key is this: the more bonds an atom makes, usually the lower energy those electrons end up. And so even though there's a little bit of an investment here in putting this electron in a higher energy orbital, but now how many bonds can we make? 4, and those 2 additional bonds more than make up for it. The overall energy will be so much lower than the little bit of energy we just invested to get there. Okay, so now we can make 4 bonds. Awesome. We got one more problem. We just talked about how bonds are overlapping orbitals. Your p orbitals, like carbon here, he's got an orbital that lies on the y-axis. He's got another p orbital that lies on the x-axis. If he's overlapping with, bonding to a couple hydrogens using these, he might, bond to hydrogen, overlap with hydrogen's s orbital right there, and hydrogen's s orbital right there. And if this is his p orbital on the y-axis, this is his p orbital on the x-axis, then what will be the angle between those bonds? It would be a perfect 90-degree angle. This, that's the angle between the x-axis and the y-axis. Ooh, that's a problem, because how many electron domains here? 4. What are the angles for 4 electron domains? Ooh, they're 109.5 degrees. And so this is what classical theory predicts, though. We got over this hurdle. He can now make 4 bonds, but the angles are all wrong. And we figured out, ooh, carbon must not be using his regular orbitals. And what carbon does is he takes and he mixes these orbitals. Now, if you look here, you know where the shape that an s orbital is spherical or that a p orbital has this dumbbell shape comes from? They're just what we call wave equations or wave functions. You've seen a wave function, so don't get scared, like a sine wave or a cosine wave or a tangent wave. Well, those are 2-dimensional wave functions. These are 3-dimensional wave equations. They're just mathematical equations. What's 1 plus 2? 3. What's 5 minus 1? 4. Awesome. I now see that you guys all know how to add and subtract. When we're doing hybridization, all we're doing is taking the mathematical equation of an s orbital and the mathematical equation of some other orbitals, p's in this case, and adding and subtracting them. They're math equations, and you're adding and subtracting them. And when you add or subtract them, it creates new functions. And so in this case, carbon mixes all 4 orbitals. And if you recall, when you mix 4 orbitals, you create how many hybrids? 4. And in this case, those hybrids are the average. They're higher in energy than an s orbital, but they're lower in energy than a p orbital because they're in between. And I created 4 of them. And I don't get creative. I just call them, I made it from an S and 3 Ps. They're called sp3s, and you always have 4 of them. And they each have 1 electron in them. And if you look at their shape, the shape of an sp3, if I draw one of them, looks a little funky. It looks like a fat p orbital on one side and a skinny one on the other side. Well, it turns out that's what happens when you mix s's and p's, when you add and subtract their mathematical equations. But what's interesting is when you add and subtract them, so if we look at 2 of them anyways, we're only going to look at 2 because I'm not a very good artist here. But guess what the angle is between them? 109.5. And I get to minimize the repulsion between the electrons and the bonds because now the angle is at a maximum. The other 2, I can't draw them. It's 3-dimensional. One of them's coming out of the board, and the other one's going into the board, and I just can't draw that very well. So I'm not going to put them, but they exist. They're there. But the key is by doing this hybridization, we've now maximized all the bond angles. And by making the angles as big as possible, we've minimized the electron repulsions. And that's the goal of hybridization. But again, I went through this whole process to explain it conceptually, because you could ask a conceptual question on this. But this is not how you want to actually figure out what the hybridization of an atom is. You just want to look, count the domains and say, 4 domains, sp3. 5 domains, sp3d. 3 domains, sp2. And get it that way. This is not the way to do that.